In chapter 5, we're going to talk about something called the Euclidean inner product. And we're going to start chapter 5 by reviewing some ideas about vectors. So you probably saw vectors somewhere in a pre-cal class. So let's get started. When we talk about a vector, we're talking about something that could be written this way. If it's in 2 dimensions, then it would have 2 components. So we would say it's an element of R2. If it's 3-dimensional, then it's going to have 3 components, which means it's an element of R3. So then if it's n-dimensional, then it would have n components. So if we want to find the length is also called the norm, or it's called the magnitude. They all mean the same thing. Then we're really asking, how long is this vector? So we're gonna actually look at this from a 2-dimensional perspective, and then you can see how that would broaden to n dimensions. So let's look at the first one. We want to find the length of the vector 0, 1. So if you think about what that vector looks like, we're always assuming it's a position vector. It starts at 0, 0. And this one's going to end at 0, 1. And we're asking how long that vector is. Now this one's pretty easy to see the length of the vector because it's a vector that lies along a coordinate axis. But if we were to find that length, it's going to be the square root of 0 squared plus 1 squared, which is the square root of 1, which we know is 1. We're always going to get positive numbers for these. We're talking about a length, and length always has to be something that's positive. Now let's do one that's a little bit more interesting, and we'll talk about where that formula is coming from. Let's talk about the vector 3, 4. Now we're talking about something that's not along a coordinate axis. So this is a position vector. And we know it's a position vector because it's not giving us a start point and an end point. Any vector we can turn into a position vector though. So this vector would look like this. Starts at 0, 0, ends at the point 3, 4. We're asking how long is that vector. So this one's a little different. Since it doesn't lie along a coordinate axis, we can't just see what's going on. We have to find really the distance between this point and this point. Well, remember it's starting at 0, 0 and it's ending at 3, 4. So we could think about this in terms of that distance equation. So if we were to look at that distance equation and plug everything in, it would look something like this. Now let's take that same definition we used before for the length and let's apply it to this vector. So if we do that here, our length, and notice the notation we're using for that is like a double absolute value. That always means you're finding the length of whatever vector is listed. So it's going to be the square root of 3 squared plus 4 squared. So you can see how we're getting the exact same thing, all because of the distance formula. And what this is actually finding, which is a distance. So this is going to be the square root of 9 plus 16, which is the square root of 25, which gives us a 5. The next problem is just kind of playing around with these ideas. Let's say we want to find a few norms. The norm of u, the norm of v, and the norm of the sum. So if we find the magnitude of u, square root of 0 squared plus 1 squared plus negative 1 squared plus 2 squared. So we have the square root of 0 plus 1 plus 1 plus 4, which gives us the square root of 6. We look at the magnitude of v, square root of 1 squared plus 1 squared plus 3 squared plus 0 squared. So this is the square root of 1 plus 1 plus 3 plus 0. Just kidding, 9 plus 0. And that's the square root of 11. Now if we look at u plus v, let's find u plus v first. So if we were to add these vectors together, notice this is a fourth dimensional vector. We have 0 plus 1 is 1, 1 plus 1 is 2, negative 1 plus 3 is 2, 2 plus 0 is 2. So there's our vector. And then if we find that magnitude, it would be the square root of 1 squared plus 2 squared plus 2 squared plus 2 squared. So 1 plus 4 plus 4 plus 4. And we're going to get the square root of 13. So we have a couple of theorems we can talk about. Theorem 5.1 is relating a scalar multiple of a vector and its norm. So if vector v is any vector in Rn and c is some kind of scalar, then if we take the norm or the magnitude or the length of c times vector v, that's the same as finding the magnitude of v and then multiplying it by the absolute value of the scalar. Now, why does it have to be the absolute value? Remember, scalars could be positive or negative. And when we find a magnitude, we're finding a length, and the length always has to be positive. So putting that absolute value around that c forces that guy to be a positive number. So let's look at an example. Let's say we have vector v as the vector 2, 1. And we're going to let our c be the scalar number negative 3. So if we look at the magnitude of c times v, then that would be the magnitude of the vector negative 3 times v, which would be negative 6, negative 3. So if I want to find that magnitude, would be the square root of negative 6 squared plus negative 3 squared. So you can see how we're going to get a positive number here. We have 36 plus 9, which is 45. And then we're going to break that down. Remember, 45 is the same thing as 9 times 5. And we can take the square root of 9 and pull it out. And we're left with a 5 under there. Now, this theorem is saying that's the same thing as if we take the absolute value of c times the magnitude of v. So let's substitute that in. So the absolute value of negative 3 is 3. And now we want to take the magnitude of vector v, which would be the square root of 2 squared plus 1 squared, which is going to give me a square root of 5. So you can see how you're going to get that same answer either way. So if you realize that some vector is a scalar multiple, you could always think about pulling that scalar out and applying that theorem. 5.2 is about a unit vector in the direction of v. So to find a unit vector is, and I like to write it this way, is 1 over the magnitude of v times vector v. So essentially what we're doing is we're dividing each component in v by its magnitude. And what's nice about unit vectors is that it's always going to have a length of 1, and this will always be in the same direction. So if you want something that's in the same direction, you do this. But if you want the opposite direction, then we're just going to negate that scalar value here. Negative 1 over the magnitude of v. And that will point that vector in the opposite direction of vector v. Let's look at an example. Let's look at 12. So if we want a vector that's going to go in the same direction of u, since they're using the u for a non-unit vector, I'm just going to call this unit vector. I'll call it v1. So it's going to be 1 over the magnitude of v. So negative 1 squared plus 3 squared plus 4 squared times vector vector u, which is negative 134. So we have 1 plus 9 plus 16, which is 26. So we could leave it that like that, or we could multiply it out. So there's our unit vector. This guy will point in the same direction of the original vector, which they called u. Now, if we want one in the opposite direction, I'll call this guy v2. Then it's just going to be the negative of that unit vector, which we called v1. So I'm just going to negate all the signs of this. And that negative will point this guy into the opposite direction. So let's graph this in GeoGebra, and I'm going to use the 3D GeoGebra. So go to Google, type in GeoGebra 3D, and it should pop up for you. And we're going to use the vector command. So when I type in vector under GeoGebra 3D calculator, I've got two options. I can put the start point and an end point. That's great if you're not starting at the origin. This one's starting at the origin, so I can just use that first option. So then my point, this is the original vector, was negative 134. So when I type in negative 134, you can see that position vector. And it's that black one right there. So I'm just rotating it. Now, let's type in our unit vector. So I'm using the same function. And our unit vector was negative 1 divided by the square root of 26. Three divided by the square root of 26. And 4 divided by the square root of 26. So there's our unit vector right there. I'm going to change the color, maybe, if it lets me. There it is. So you can see it's right on top of that black vector, and it's much smaller because it's going to have a length of 1. We said the vector u was square root of 26, so that was a pretty big length compared to the length of 1. And then if we were to negate everything in that vector, you'd see how it would go in the opposite direction. So let me go back and edit so you can see that. So I'm going to get rid of that first negative, and then basically multiplying everything through by negative. And then when I did that, you can see how that vector is now in the opposite direction of the original vector, and it would also be in the opposite direction of that unit vector, all because those signs flipped. So we multiplied everything through by a negative. So that's what's going on behind the scenes. So 16 has a different flavor to it. It's asking us to find the vector with a given length that's in the same direction as this vector. So here's the way I'm going to approach this. Now I want this vector to end up being 3 units long in the end. And I want it to go in the same direction as u. So let's start by finding the unit vector associated with this, and then we can just multiply it by the magnitude 3. Sounds simple enough, right? So if I find that unit vector, so I need 1 over that magnitude of u, which is 0 squared plus 2 squared plus 1 squared plus negative 1 squared, times that vector. So that's going to be 1 over the square root of 6 times our vector. So our unit vector in this case would be 0, 2 over square root of 6, 1 over square root of 6, and negative 1 over square root of 6. Now, I'm going to leave the square roots in the denominator. You could rationalize if you want to. It does not bother me if you leave square roots in the denominator. I know we were real big about that in trig, but once you get past trig, we usually say it's okay to do that. So we have a unit vector. We know this guy has a magnitude or a length of 1. And we also know it's in the same direction as that original vector. If we want this vector to have a length of 3, then all we have to do is multiply it by 3. And we're actually using theorem 5.1 to kind of help us do that. We know that the magnitude of some scalar value times a vector is equal to the absolute value of the scalar times the magnitude of the vector. So if we were to multiply this guy by that magnitude that we want, that ends up being our scalar value here. So 3 times our unit vector. Then we're going to get the vector. Oops. Zero, 6 over square root of 6, 3 over square root of 6, and negative 3 over square root of 6. So there's a vector that has a magnitude of 3 that will be in the same direction as you. Now, if we were able to graph this in 4 dimensions, which we can't. GeoGebra can't do anything in 4 dimensions. 4 dimensions gets complicated to graph. We would see this vector. We could graph the unit vector, which would have a length of 1. And we would see that this guy is going to be 3 times as long as the unit vector and in the same direction as you. So that's visually what we would see if we were able to graph. Unfortunately, we're not in 4 dimensions. So what if we wanted to talk about the distance between 2 vectors? How far apart are they in 2 dimensions, 3 dimensions, or n dimensions? To find the distance between 2 vectors, then we would take the magnitude of the difference of the vectors. So notice the notation they're using for distance here. They're using that small d, which means you want to take the distance between those 2 vectors. So let's apply that definition. If we look at these 2 in 3 dimensions, the distance between u and v would be equal to the magnitude of u minus v. So I'm going to take vector u, and I'm going to subtract vector v. So 1 minus negative 1 is 2. 1 minus 3 is a negative 2. 2 minus 0 is 0. So then that magnitude would be the square root of 2 squared plus the square root of negative 2 squared plus the square root of 0 squared. So this guy is the square root of 8. We can break 8 down into 4 times 2. We know the square root of 4 is 2, so we can pull it out. You should always simplify these radicals. So we're going to get 2 square root of 2. That's the distance between these two vectors. So if we were to look at what's going on in GeoGebra again, we can graph both of these vectors in 3 dimensions. So I've gone back to GeoGebra. The first vector was 1, 1, 2. The second vector was negative 1, 3, 0. I'm using that vector feature again. Make sure you have that double parentheses there, so that it knows that the ordered pair you're looking at for the endpoint for vector v is negative 1, 3, 0. So in space, there's my 2 vectors. When we find that distance, we're actually finding the distance between the tips of those vectors. Remember, vectors are not the same thing as rays. If you think back to geometry class or somewhere where you talked about geometry, rays keep going forever and ever and ever. Vectors stop. They have a magnitude and they have a direction. So there's a little distinction between those two. So if we were to look at the tip of that black vector and the tip of that red vector, that distance is what we're finding here. And that distance in this case happens to be 2 square root of 2. Now there are a couple of properties of distance that we need to be aware of. First off, anytime we talk about distance, we're always going to get a positive number. You can never get a negative number. It is possible we could get a distance of 0, but the only way that can happen is if those vectors are actually equal to each other. And also, order doesn't matter. The distance between 2 points is going to be the distance between, the distance between 2 vectors will be the distance between 2 vectors. It doesn't matter if we go u minus v or v minus u. That distance is going to stay the same regardless. So now we're going to move on to that definition of a dot product. And the definition of a dot product is going to give us something that's going to give us a scalar value. Remember, scalar is just a number. So the dot product in this case, if we take u dotted with v, it's going to be u1 v1 plus u2 v2 plus u3 v3 and so on. These vectors have to live in the same world in order for this dot product to exist. And what I mean by that is they have to both be in Rn. So we have to have either 2 two-dimensional vectors, 2 three-dimensional vectors, or so on. We cannot mix and match dimensions. They have to be from the same dimension. So let's look at a couple of properties of dot products. Because we are looking at multiplying real numbers together and then adding a whole bunch of these numbers, the dot product is going to be commutative. So your commutative property says it doesn't matter if I do u times v or u dot v or v dot u. I'm going to get the same value either way. And that really has to do, like we said, with the properties of the numbers that's inside of here. There's also an associative property. Just kidding. There's also a distributive type property. If I take u dotted with v plus w, it's the same as u dot v plus u dot w. And then we have a scalar value property. So if I take a scalar times the dot product of uv, that's the same as a scalar dotted with, the scalar multiplied by u dotted with v, or u dotted with the scalar times v. Notice we are not putting that scalar with both of those, only with one. And then 4, if I take v dot v, that's the same thing as the square of the magnitude. I'll get the same value either way. So a lot of formulas in this chapter, we could see them written this way or this way. And then v dot v is always going to be greater than or equal to 0. If I take a vector and I dot it with itself, I'm going to get a whole bunch of things that I'm squaring. And the only way it can be equal to 0 is if we're starting with the 0 vector. So I want to go through and I want to prove some of these just so you can kind of see what they're talking about a little bit better. And I'm just going to do 3 dimensions. We could do n dimensions. You would get the same results. We could do 2 dimensions. You could get the same results too. So let's look at that first property. If I take u dot with v. So if I were to dot these two together, I'm going to get u1 v1 plus u2 v2 plus u3 v3. Now if I were to take v and dot it with u, I would get v1 u1 plus v2 u2 plus v3 u3. Now these are almost the same. What's different is that order. But we know at this point we're dealing with real numbers, and we know real numbers are commutative under multiplication. So under the commutative property of real numbers, this guy is equal to this guy, and that is identical to u dot v. And I want to look at 3. So if we take c, which is a scalar value, so we're going to let c be a scalar. So we have c times that dot product. So we're going to have c u1 v1 plus c u2 v2 plus c u3 v3. So that's if we were to distribute that c. That's your distributive property of real numbers. Now, we can change the grouping because we are associative under the real numbers. And that would be the same as CU1, CU2, CU3 dotted with V1, V2, V3. So we're undoing that dot product. So that would be CU dotted with V. So you can see how that scalar value only goes to one of those vectors, not two. Now we can actually pick up from here. So I'm going to say and. If we were to change that order, we're dealing with real numbers inside of this, so we can change the order because of the commutativity. commutativity property of multiplication of real numbers. And then now we can change the grouping and put those C's with the V's. That's an associative property. And then we could pull apart that dot product. So then that's U1 dotted with C times V. And then I want to look at the proof for 5. If we take V and dot it with itself, so we would have V1, let's write it out first. V1, V2, V3, dotted with V1, V2, V3. So that would be V1 times V1 is V1 squared. V2 times V2 is V2 squared. V3 times V3 is V3 squared. So anytime we square a number, we end up getting a positive, which means that this guy has to be greater than or equal to 0. Now, if I'm adding a whole bunch of positive numbers together, then the only way that this guy could possibly be equal to 0 is if V is equal to 0. So you can see where that property, that fifth property, is coming from.